let's go through the assignment and make sure we're all on the same page with the answers and stuff. So, how did you guys feel about the content? Not so much how difficult the assignment was, but did you learn anything interesting?
Well, I kind of heard that the flood happened and it didn't happen because they said that it was because the rock was metamorphic, but it wasn't metamorphic because it was sedimentary rock, so it couldn't have just been like bent like that.
Yeah. So basically the whole article is about a single data point that is worth exploring, which is that we have these layers of sandstone rock, which is a sedimentary rock, and they are bent like this. This is basically a hill. This is a cross section of a hill looking down. And did you notice there's a person in the photos in your article? It's very hard to tell even in color. And I printed them in black and white. The two photographs, not like the diagrams, but the two photographs, both feature people in them. You found one, Isaac? Where'd you find it? Found both. Yeah, it's like Where's Waldo for creation science class.
Where's me? Where's Waldo?
Yeah. And the reason I call that to your attention is because a lot of times when you're looking at pictures of rocks, it's very hard to get a sense of scale. Are we looking at something under a microscope? Are we looking at something sitting on the counter? Or are we looking at something that is 100 feet tall? And the answer is more like the last one. There's some very small people. In the first picture on page 4, you can see the person just a little bit to the right and a little bit below the center. And then the other one on page 5, actually the person's almost in exactly the same spot on the square.
Oh, dang.
A little right and a little south of center. Yeah, very small person. So it gives you a sense of the scale of these photographs. And the problem that they're outlining here is that rock, have you ever tried to bend a rock? Suppose the rock started out straight. It starts like this, all the way across, and then something happens to it and it bends. What would you expect to find if a whole bunch of rock suddenly went from this to this? Yeah?
Well, it would probably have to be really hot rock that was lava.
Well, suppose it wasn't. There's no evidence that it was hot, so we won't even go there.
Then it would be really hard to bend it.
It wouldn't bend, right? Have you ever tried to bend a rock?
It would either break or you just wouldn't be able to bend it.
Right, so obviously something was able to bend it, so that's out of the question. But yeah, if it were bent, it would be cracked. It would be filled with cracks, all through the length, all along the edges. The pieces would not flow smoothly like this. They would be more like a bunch of rectangles all together. And the fact of the matter is this is not what we observe. Instead, what we observe is that the many layers of rock are all smoothly bending along contours that are sometimes 90 degrees. Which one is it? The first photo on page 4, it has a U-shaped bend that if you turn your paper sideways so that one side of the U is flat, the other one is almost straight up and down. It's very close to 90 degrees, which is a tight bend. And in fact, the bend right next to the guy, some of those are 90 degrees. They make like a backwards letter L going away from the guy to the right and then upward. So these rocks are bent without cracking, which itself is not that big of a deal, because these are sedimentary rocks. Who knows what a sedimentary rock is? Andrew?
It's a rock that's made out of sediments that were in the
rock that's made out of sediments, yeah.
And it gets put together in a river bottom or something like that.
Yeah, so it's a rock that is formed by a whole bunch of little bits and pieces of stuff falling together, and over time, as the pile gets really high, the stuff at the bottom pile has a lot of weight on it. So the stuff at the bottom of the pile has a lot of weight on it, and that weight compresses it and causes it to harden and form a solid rock. And that's what we have here. It's just layers and layers and layers of sedimentary rock that has been compressed and hardened into place. Now, what this tells us I should erase the cracks and make it what we actually see. What this tells us is one of two things. because we see these layers, which clearly used to be flat, and now they are like this, they're bent. What this is telling us is one of two things. Either all of these layers were still soft when they were bent, right? So if they were deposited into different layers, where like the more dense deposits would be at the bottom and the lighter ones would be at the top, they were all deposited, and then the layer was bent while they were still soft, and then they hardened. That's a possibility. Or the other possibility is that they were heated very, very hot, and rock that is heated, it doesn't have to melt and become lava. It would still be extremely hot, but if you heat it up enough, before it melts, it becomes pliable and it's able to bend. And so the only two explanations for how this could happen, and this is what we observed, the only two explanations is either all of these layers were still soft at the same time when they bent, or they were very, very hot. And the article concludes saying that there's actually a way to see if it was really hot, because there's another kind of rock. Have you guys learned the three kinds of rocks in earth science class? You got your igneous rocks, which are cooled lava, your sedimentary rocks, which we've been describing, and then your metamorphic rocks, which will actually change from one form into another under heat and pressure. And so if this sedimentary rock were actually hot enough to move, there are bits of metamorphic rock impurities inside of it here. And these impurities would have turned from their lightweight, low temperature form into their heavyweight, high temperature form. So there is a way to test, did this happen due to heat? And the answer is no, because these metamorphic rocks have not been hot enough to change, to metamorphize. Metamorphosize? It's been a long day. These rocks haven't changed the way they should if it's really, really hot. And so we know then that the only reason this could have happened, the only way this could have happened, is if all of these sediments were bent while they were still soft, before they had hardened. And that also means that all of these layers were soft at the same time. And that goes against a major assumption made by people who think the Earth is billions of years old, which is that these layers were deposited very, very slowly over millions of years. Ask a long-age geologist to analyze these layers, and he would come back and tell you that, these layers were formed 200 million years ago, and these ones were formed 180 million years ago, and these were formed 160 million years ago, and, they have ages for each of these layers. But that can't be true, because the layers could not be soft for millions of years while we wait for more of them to pile on top. So the commonly accepted geologic explanation for that observation is not true. It doesn't fit the data. It's not scientific. And the only reason it is put forth is because it confirms the narrative that is, the Earth is the Earth is old, and uniformitarianism is the name of the thing that we'll be attacking later on. But yeah, uniformitarianism is like the bane of modern science, and it says that that everything happened as slowly as it's happening now, and so this feeds into the dating discussion we're going to pick up. So if we can measure how fast it changes now, and we measure what we have now, and we assume that it started at some kind of zero, depending on what we're dating, then all you have to do is multiply the rate by the time, and you get how old it is. But the problem is we don't know how fast it was changing over time, like 1,000 years ago. We only know how fast it was changing now, and maybe like 50 or 100 years ago tops. Sorry, I think I'm getting ahead of myself. Let's look at the questions and make sure the questions are understood. How high above sea level is the plateau through which the Grand Canyon runs? Yeah?
70,000 to 8,000 to 8,000 feet.
Very good, 7,000 to 8,000 feet. And we're talking about the Grand Canyon because the Grand Canyon is a place where you can actually see these layers. It's a big, tall plateau of sedimentary rock, and then right in the middle of the plateau, somebody cut a great big long canyon. If you've ever been there, it's a lot more complex than a single canyon. It has branches, and It's massive. Words can't do it justice. It's beautiful and big, and it also gives you an inexpensive look at the different rock layers that make up that particular plateau. How long ago do old Earth advocates believe the first deposits of the Grand Canyon were made? And if you don't have the right answers on these, you're welcome to change them before I collect again. Somebody besides Andrew. Riker?
520 million years ago.
520 million years ago, right. So the first deposits, of course, are the ones on the bottom, and they would say this is 520 million years old, and then everything builds on top of that. And then how long ago do they, that is the old Earth advocates, how long ago do they believe the bending of the Grand Canyon rock deposits took place? Andrew?
60 million years.
60 million years ago, right.
Oh,
So 520 million years ago, this lower layer was deposited, and more layers were deposited as the eons turned. But then this happened, I should be labeling these. So 520, was it 520 million years ago? I'll put YA for years ago. And then this was, what was that number, Andrew, that you just read?
60 million years ago.
60 million years ago. So yeah, so this bending took place 60 million years ago, according to the old Earth advocates. And number 4 is it's a loaded question, so I'll just read it. The old Earth model claims that the Tapete sandstone, which is the lowest thin rock layer in figure 1, so that'd be a hint to go and look at figure 1 in your book, which is this one, and you can see Tapete sandstone is like the lowest thin layer, I said. There's a bedrock layer beneath it, but the Tapete sandstone is the lowest thin layer in that figure. The old Earth model claims it was deposited 460 million years ago. What would have happened to that layer if it were bent and folded after hardening into solid rock? And then I have a hint. Consider what happens to concrete if it gets folded after the cement is set. Yeah?
It would crack and break.
It would crack and break, right. Fracture is the geology word there. And and yeah, that's what happens to rock that you try to bend. So that's the only thing that could have happened if the old Earth model were true. But the old Earth model appears to fail to address the actual scientific observation being made. Number 5, according to the creation model, how long did it actually take for all of these rock layers to be deposited and bent? Anyone else got that besides Andrew? Ivy? Less than a year, very good. That's on the top of page 3. I should be noting where these answers are coming from. They're all from the article. The last one was the second paragraph on page 2. This one's at the top of page 3. Yeah, and then leading right into number 6. According to the creation model, what biblical event caused all of these rock layers to be deposited and bent? Andrew?
The flood. Right,
Noah's flood. Remember, Noah's flood was worldwide, so it did not just rain in Israel or wherever Noah happened to be living over in the ancient Near East. It was global, everywhere in the world. And so we should be seeing evidence all over the world of rock layers being deposited, sedimentary rock layers being deposited by water. And these layer formations should be huge. They should span continents. And you know what? We do. That's exactly what we observe. So you could make predictions based on Noah's flood narrative and then dig for them, and you would be spot on. That's what we see. Number 7, I kind of beat that horse to death, but why can't these rock layers have been bent by heat and pressure, as old Earth advocates suggest? Riker?
It would have turned into quartz or different metamorphic rocks.
Very good. So, so there are, I think it's metamorphic impurities. It's been a while. I didn't reread the article before I gave it to you because I picked it up last year. There were quartzite, marble, and other metamorphic rocks appear after their predecessors. Limestone for marble. I forget what the quartzite predecessor is, but you got a precursor rock and you subject it to heat and pressure, and then it turns into a different kind of rock and metamorphosizes. And we don't observe that happening here, which means that these rock layers were not subjected to heat and pressure, which is the only way to explain their shape if you follow the old Earth narrative. And then number 8, this is just kind of tying it all together. The Tapete Sandstone Formation, remember that's the bottom layer in that figure, that sandstone formation can be traced from North America across northern Africa, so like on the other side of the ocean, to southern Israel. What is the only explanation for how sediments could be deposited in thick layers across several continents, one after another, in rapid succession? Andrew?
A global flood.
Very good. Only a global flood cataclysm could carry the sediments to deposit thick layers across several continents, one after another, in rapid succession in one event. I would just accept global flood cataclysm. I think I just copied and pasted that whole sentence from the article. That's the last sentence in the article. Explains that. So yeah, as far as scientific reading goes, I thought this was a fairly easily digested article that tackled one thing that is observable even today to the casual person. You can go and climb on these rock layers that have been bent, and you learn something about biblical history that way. Okay, now I'll take your papers back. Today, so I wrote down some of the things that you guys said were evidence that you had heard for an old Earth, and I wanna revisit that today, and we'll just kind of take it from there. Let me see here. So we're going to talk about carbon dating. We'll talk about fossils and dinosaurs and glacial ice cores. And honestly, they all of those topics circle back around to dating, which we talked about last time. So I'm going to review that because it is, it's algebra. We're going to talk about that and then and review that and then talk about how that fits into these other things. So the mathematical equation for dating something is, and this is very general because the something that we're dating can be like anything. I'll get to some examples in a moment, but we observe what we have. So this is solid. Anything that we have right in front of us and we can measure and experiment on, that is like the best kind of observation you can get in science. How it started, so what we have equals how it started plus how fast it changes times the time, that is how long it's been changing. So if we measure what we have and we measure how fast it's changing, then you can figure out how long it's been changing, assuming you know how it started. And that is the gist of it. So one dating example you guys mentioned last week was counting rings on a tree, right? So if you know that a tree makes a new ring every year, the spring season comes around and it grows another layer of bark and the one behind it becomes a ring, then you can cut a tree down and you can look at the cross section and count the number of rings. And if it makes one ring per year, we have how fast it changes. One ring per year. I'll throw that in there for this example. One ring per year. And how did it start? How many rings does a tree have when it first hatches from a seed? When it first sprouts from a seed? One. Yeah, I'll go with 1. I would also accept 0. But the point is that we know how it starts. We know how trees grow. We have observed trees growing, and it's safe to say that any tree that we haven't observed growing probably follows the same pattern of, sprouting from a seed with 1 or 0 rings. And so then it's easy to see if we have, suppose we have 20 rings. Okay, 20 rings. So you cut down a tree, you count the rings around the core of the trunk, it's 20 rings, and it grows 1 ring per year and it starts off with 1 ring. How old is the tree?
1 year old.
1 year old, huh?
20.
20, or 19 technically by this equation, but yeah. If it starts with 1 ring and it grows 1 ring per year, then you would subtract 1 from both sides to get 19 rings equals 1 ring per year times time, and then you would divide through by 1 ring per year. And you would get 19 years equals time. So the tree's been growing for 19 years. And that's how dating works. That's how tree dating works. That's how ice core dating works. That's how carbon dating works. That's how uranium lead dating works. All of the different dating methods use this equation, this magical red equation. Sometimes it's a little more complicated, like the radiometric dating. How fast it changes is actually in half-lives, which you really don't need to know this. But just know that it's a little more than super basic linear algebra. This is the general, this is how it works. This is how we date things. With the tree rings as a good example. There are some bad assumptions built into this model, though, that we talked about last time. Who can remember one of the assumptions we have to make that maybe we shouldn't be making?
Isn't it that for like carbon dating, that like the atmosphere wasn't always the same as it was now?
Very good. A bad assumption is we know, and I'm just going to put it in brackets here, how it started. For example, suppose Adam in the Garden of Eden had chopped down a tree. What do you think he would find in that tree? I bet he would find rings.
Yeah.
Yeah. So, but the tree was made 3 days ago. So, if Adam finds 20 rings in a tree that grows 1 ring per year, does that mean the tree's 19 years old?
No.
No, right. So, and the reason why that fails is because we don't know how it started. That is a bad assumption. When you're dealing with trees, it's a pretty good assumption for us. I don't think there are any trees in the world that are over 4,000 years old. So, pretty good assumption for us. But that's only for trees. If you're looking at a sample of rock, there's no reason to believe, for example, that the rock was originally 100% uranium, and that the current mixture of uranium and lead in the rock is relatable to how it started. Because if God made the rock with a mixture of uranium and lead in it, which he probably did, because God did not make a baby world. God made an adult world. The trees were adults, Adam and Eve were adults, everybody was an adult. Hello, my adult wife.
Yes.
You're on TV.
Okay. There used to be a bucket of scissors out here that were from the basement.
Try looking in the closet. I think a lot of stuff got moved for the Reformation event.
Okay.
So I saw some stuff in the closet. Yeah. Sorry about that. Logistics. Right, so we don't know how it started. And with carbon-14, that's important because carbon-14 assumes that we know how much carbon-14 was in the atmosphere 50,000 years ago. And we don't. We don't know. We have no idea how much was there 50,000 years ago. It's a guess. It's not a total guess. There's circular reasoning involved. What they'll do is they'll find a rock layer that they have already dated to be 200 million years old, and they'll measure something like a diamond in the rock layer. Diamonds have carbon atoms, and they'll measure the composition of carbon atoms in that diamond, in that layer. I guess it wouldn't be 500 million years old, because carbon dating doesn't go that far back. But let's say we got a higher layer, and they know it's 100,000 years old. And so they'll mine a diamond out of that layer, and they'll test its carbon composition, and then they'll work it in. So there we have what we have and how fast it changes, and we work back to see how it started. And so then we say, okay, so then 50,000 years ago, the atmosphere must have had this much carbon-14 in it. And I'm getting a little bit ahead of myself. Sorry, but the fact of the matter is it's circular, because we don't know how old these layers are. And so how can we use that age to determine, these other things? When everything is built on faulty assumptions, all it takes is one assumption to be wrong and the whole house of cards comes falling down. I'm gonna come back to carbon dating in a moment. This is still the review section. What's another bad assumption about this equation? Andrew?
we know how fast it changes because we don't.
Very, very good, yeah. We actually, here, a better way to say it is this. How fast it changes is constant. Oh, I think I have another assumption too. But yeah, so we think how fast it changes is constant. You remember last week, I hope, the example I gave you of the water dripping into the buckets and how we measured the rate of dripping, and we measured how fast it changes, that's the rate of dripping, and we measured what we have in the bucket, and we assumed that it started empty, and then we figured out how long the bucket had been sitting under the drippy faucet. But what we failed to take into account was that somebody turned on the faucet really hard for a few minutes before you came into the room, or that the bucket already had water in it when it was set under the faucet, or that it had been sitting under the faucet for a long time, and then somebody picked it up and dumped the water out and set it back empty, which I guess would reset it. It wouldn't technically violate your assumptions. But the point is we do not know that the rate of change of anything is constant. The best we can do is radioactive materials in a laboratory setting are extremely predictable in how they will break down, and that's why radioactive materials tend to be fodder for dating, because we assume that the laboratory settings are the same as they are in nature. But that's still a big assumption. We do not know how fast something changes. And this assumption actually has a name. I've already said it, so I'll go ahead and write it down now. Uniformitarianism. It's a really long word and has nothing to do with wearing a uniform. What it means is that the rates of change that we observe today are the same as they have always been. So it's like a fundamental assumption in geology, in the study of rocks. Basically, the way Dr. Stacy Lung explains it, I'll see if I can get her to come in sometime. I haven't asked her to come in this year, and I don't know. I feel like I have feelings that I just need to get over and ask her, because she is really good. When she came in last year, she answered a lot of the kids' questions. And she liked to say, or the way she told it was that geology basically hit a standstill like 150 years ago, where scientists were like, we don't know what all these rock layers mean. We don't know how to interpret them. And a guy, I forget his name, famous scientist guy, came up with this idea of uniformitarianism, and he said the present is the key to the past. And so if we measure the way things work now, then we can work backwards with that measurement to figure out the past. So as an example, suppose you've got a river that is eroding the rock layer. So here's a river, and then here is the layer of rock at the bottom of the river. And the water's flowing downhill, and as it flows, it takes some of the rock with it, so that over time, the river gets deeper, essentially, because it's taking its bottom. Imagine it's a sandy bottom. It's just carrying the sand off the bottom down into the ocean. And so every year, there's a little bit less sand on the bottom as it gets eroded away. And so uniformitarianism says this is the way it's always been. If you can measure how much sand is being removed year over year, then you can assume that is always the rate at which sand has been removed from this river. And it's the same thing. How fast it changes, in this case, is how fast the dirt is being taken off the bottom of the river, or the sand, the rock, whatever it's on. And you just work backwards to see, how, assuming, I guess, that the zero position is when the rock is the same level as the water. I don't know. It's different for different aspects of geology, but the bottom line is uniformitarianism is the assumption that if we measure how fast a thing is changing now, then we can assume it has always changed that fast. And especially if Noah's flood is real, that is a huge change that happened a long time ago, and the Earth has kind of been recovering from that change as time goes on until we get to now where the Earth is, more or less stable. And if we assume that it's always been more or less stable, then we're going to take it back in time theoretically and come up with something vastly different than what actually happened. And that's really it. There was this massive global flood that happened 4,000 years ago, roughly 4,500 years ago, and the evidence of that flood is everywhere. But because we've never observed a massive global flood since then, something about God promising never to send a massive global flood again, because we've never observed anything like that, we can't really take it into account with our predictions unless we assume that it happened. And scientists don't like to assume that the Bible is right if they can help it. It's 6:37 right now, if anybody's curious. That clock doesn't work. I should just get rid of it. But it has a plate on the bottom. That means somebody donated it. So, so I can't just get rid of it. I've put in new batteries and it doesn't work. It's working. I mean, it's got a second
move
hand.
the hands or anything?
You can, but it doesn't keep time. Go ahead, move the hands. It's 6:37. Make it 6:37.
Oh, I haven't worked with that. I haven't worked with that.
The bottom one.
By this time next week, just move the minute hand, not the second hand.
Oh yeah.
Actually,
So
maybe it doesn't matter.
6:37, something like that.
Right now it's 12:37 on that clock.
Oh.
Maybe you can just move the little hand down. Whatever, it's broken. You'll see what I mean. Next week you will, because next week it will say the wrong time.
Shoot, I completely forgot how to do time. I think that's it. I did not sleep very much last night.
Okay, yeah.
I didn't cook.
Okay, the last, so technically the little hand should be like halfway between the 6 and the 7, because the minute hand is halfway through the hour, but whatever.
It's fine. So it won't be accurate?
Yes, it won't be accurate by next week.
Are the seconds, like, not seconds?
Yeah, the seconds are not seconds. That's one way to think of it.
Oh.
There's probably some relation to dating and time and rates here that I'm not getting because I'm tired and sick. But yeah, there's some. I can feel it. There's some really good joke potential here, and I'm not giving it to you. So my apologies. Darn it! Now I don't remember what my third assumption was that I wanted to say. We know it started. Speed of change is constant. And, oh yeah, and nothing happened in the interim. So, an excellent example of this that kind of piggybacks into one of the things I wanted to talk about today is ice cores. Okay, so at least one of you has heard that ice cores reveal that the Earth is very, very old. And in case you don't know, I'll get out my blue marker for this one. The way they do this is they find a glacier that is made of ice, as glaciers tend to be. And underneath this glacier somewhere is the ground. And then this glacier is very, very thick. It covers the ground like up here and stuff. Maybe there's like a guy skiing down the glacier or whatever. There we go, yeah. Going down that glacier there, that's actually too tall. The guy's way too big. The glacier is very, very tall. And rather than skiing down the glacier, what scientists do is they will drill into the glacier. They have a specific technique for drilling that will remove a core, remove a big cylinder from the glacier. So something like this. Go all the way to the ground, sure, why not? And when they pull out the big cylinder, what they find is that the big cylinder has layers in it, just like the rock layers there. There are layers where you can tell there's like different kinds of snow falling. Some of them are thick, some of them are thin, and they say that each one of these layers corresponds to 1 year of ice deposition. So we'll say 1 layer equals 1 year. So every year, you get a new layer of ice on top. And if you count up all the layers, there's like tens of thousands of them. So that would imply that the glacier is tens of thousands of years old, right? Now, what happens though when, and this is a true story, this was found fairly recently, buried in the glacier under several thousands of years of layers, they have found a crashed World War II era airplane.
Well, that's not thousands of years.
Yeah, exactly. So you can't test you can't test this theory without spending literal thousands of years, but you can find something that contradicts it, and then it's like, that kind of turns the whole thing on its head. And actually the reason I started talking about ice cores right now was because I wanted to highlight this nothing happened in the interim assumption. Because suppose there were a bunch of ice layers, and then there was a melt, there was a thaw, there was a warm year, and several thousand years of ice layers just melted and washed away. You'd never know it, because the next year it got cold again and we got a new layer. And so that assumption there that nothing happened in the interim is just not true. It's a bad assumption. And that particular assumption, I think, would actually cause you to make it look younger than it really is. Because if you lose thousands of years, then you're going to end up with a younger estimate than reality is. But the story of the plane and the ice cores, not the ice cores, the story of the plane in the glacier is real and definitely calls into question the assumptions that we make. And it has also been observed in surface level ice cores that the layers actually change. You get multiple layers per year. A new layer forms every time it snows, basically. You get a bunch of snow and it makes a layer. Yeah, so the assumption that one layer equals 1 year, that's assuming that we know how fast it changes. We know that every year 1 layer of ice gets deposited in the glacier. Well, if that ends up being untrue, then again, that's going to give you vastly inflated ages for your ice core. So that's the long and short of ice cores. It's the same basic principle. We have an ice core. We assume it started at 0, no ice, and we assume we know how fast it changes.
Well,
and from those assumptions, we get this equation, and we come up with a time. Yeah?
Well, couldn't have God made the Earth with already the ice?
Oh, I didn't think of that one. Yeah. Yeah, who's to say God didn't put glaciers on the Earth that already had layers? He very well could have. Creation scientists generally believe that there have been several ice ages since Noah's flood. You know how I was talking about Earth, having really unstable activity after the flood? One of the things that would have been unstable would be the climate. And so you would have an ice age where, say, creatures could walk across a land bridge to Australia, and then the land bridge be cut off, and so that's why all the creatures in Australia are weird, because they've all been isolated from the rest of the world and have developed their own way. We'll talk about evolution in another class.
Is that why there's not? Is that like Native Americans came to America?
Yeah, there is a mainstream theory about Native Americans coming to the United States from Russia, from Asia, over a land bridge or possibly a glacier that gave a walking path between the eastern edge of Russia and the western edge of Alaska. Yeah, so this is not an out there idea. I will admit, mainstream scientists laugh when we say that the Earth was ever flooded a long time ago. Even though there's all this evidence, it's too much for them. But they are generally willing to accept a lot of the other things that we put forth, like how there were ice ages in the past where the Earth was much cooler than it is now, and that there were land bridges that allowed creatures and people to get places where they can't get anymore by that route. For example, walking to Australia from India, or walking to Alaska from Russia, that kind of thing. Oh, I had something else to say, but I lost it. Andrew?
So for skin color, is that did God make people with different skin colors, or was that kind of like an evolution?
He probably gave Adam and Eve a skin color that was quite a bit browner than any of us has. But within the genes of people of brown skin are browner skin and lighter skin. There's at least one case of twins born to a couple in India who both look like your typical Indian people, fairly middling brown colored skin. And these twins, one of them is very dark black and the other one is very white. And it's just because the genes, they're fraternal twins, not identical, and it's just because the genes for skin color exist in the human genome and can be expressed like that. I believe the darker skin tends to be a dominant gene, or, no, I don't actually know that. I'm not going to say that. But
because, like, two white people...
Yeah, they're not gonna make a black baby.
Yeah.
Mm-hmm. Yeah, that's some Maury stuff that we won't get into. That's a bad TV show. Don't worry about that. But where was I going with all that? Yeah. So generally, I think we've talked about this in this class before, but maybe not. We're getting a little into evolution now, which is a whole nother bag of worms that we're not gonna look at too much today. But the long and short of it is, people with darker skin tend to do better in climates with a lot of sunlight, like near the equator of the Earth, like, I don't know, the Sahara Desert in Africa and places like that, where there's a ton of sunlight and the darkness of your skin helps to block some of the harmful rays of sunlight, whereas us white people would fry, we would burn, and it wouldn't be good for us. So darker skinned people tend to thrive better in the equator, equatorial regions of the Earth. Whereas farther from the equator, there's a lack of sunlight for half of the year. We are entering that half of the year right now here in Minnesota. And the dark skin then becomes a bad thing for survival because it is blocking some of the helpful rays of the sun that your body needs to make vitamin D and stuff. And so populations that are historically from places farther from the equator tend to have lighter skin because those are the ones that are more likely to survive there. And the only known exception to that general rule are the Inuit people in Alaska. They have dark skin, but they live all the way up in Alaska. And the thinking is that because they eat mostly seafood, and seafood is a good source of vitamin D, that they are able to survive that way and get the vitamin D another way. Was I cutting you off, Andrew?
Oh no, I was just gonna say, like albino people, that happens sometimes, but that's just like a...
Yeah, so albinism is a mutation. I forget exactly how it works, but that's different than just a population historically drifting in the color of their skin over time. We'll get to that when we talk about evolution. You're going to learn more about evolution in this class than you've probably learned in school up to this point, because you have to understand evolution before you can understand what's wrong with it. So I always say that people who believe in creation should be experts on evolution, because you have to. You can't say something is wrong if you don't understand what it's saying. Okay, tying up some loose ends here. I said I would talk about carbon dating. So I'm going to erase my Tapeats sandstone here. And I told you about how radioactivity works, where an element has a certain makeup, like an atom, a single atom of something has a certain makeup, and then something flies off of it, and now it's different. That's what radioactivity is. And carbon dating uses a specific kind of carbon called C14. And carbon, is it 8 protons are in carbon? Hydrogen, helium, lithium, beryllium, boron, carbon, right? That's 6.
Yeah,
okay.
6 is. Because we were just talking about that today in science.
Okay, very good. So, gosh, I had to count it on my fingers. I feel like a beginning math student or something. So we're gonna make the protons here red, and a carbon atom has 6 protons. So here they are, 6 protons. That defines an element. If you looked at a periodic table before, the elements are defined by the number of protons that they have. But if you've ever learned about atoms, you probably know there's not just protons up in that business, there's also neutrons. and I'm going to make neutrons black here. And the 14 in C14 refers to the total number of protons plus neutrons in it. So if it's got 6 protons, it's going to have 8 neutrons. 1, 2, 3, 4, 5, 6, 7, 8. There we go. And it turns out this is a little too big. The carbon atom, and there's electrons too, but they have like almost no mass. So we ignore electrons a lot of the time. And they pop off pretty easily. Chemistry. But turns out C14 is a little bit too big. And there's a whole cycle here that I forget what it is, but eventually it ends up with carbon 12. There's probably not even that many steps in the cycle actually, because what will happen is we'll lose a neutron here, and then it'll be carbon 13, I guess. I should have looked up the whole cycle. But at some point in this cycle, we lose 2 neutrons. There they are. Bye-bye 2 neutrons, and we end up with carbon 12. This is stable. And in a laboratory setting, the rate at which this becomes this is able to be measured. And it's in the half-life of carbon-14. Remember I mentioned how it's a little more complicated with radioactivity. So if you have a sample of mixed carbon-14, let's start over. If you have a sample of carbon-14, pure carbon-14, and you just let it sit after, I'm going to say 50,000 years. I'm probably wrong on the half-life, but just for the sake of an example, after 50,000 years, your pure carbon-14 will be 1/2 carbon-12, and the other half carbon-14 still. That's what a half-life is. And then, if you wait another 50,000 years, it will not be down to 0, it will be down to 1/4 of the carbon-12. 1/4 carbon-14 and 3/4 carbon-12, because, let me draw it out here. So here's your box full of carbon-14, and after 50,000 years, you now have carbon-12 and carbon-14, and then after another 50,000 years, half of your carbon-14 is now carbon-12, and the other half is still carbon-14. And after another 50,000 years, it's still not 0, but instead you've got half of that turns into carbon-12, and the other half is carbon-14.
Well,
and so
it'll never reach 0.
Right, yes, it approaches 0 asymptotically is the calculus word. This is calculus now, not just algebra. But yeah, it's still the same principle though. You can measure the ratio of carbon-12 to carbon-14 in your sample, and you can backtrack it with this supposedly known rate and get back to how it started. But an important thing to note is that you have to know how it started. You have to know all 3 of these things in order for this equation to work. That's basic algebra. If you have an equation of one variable, which is time, this is what we always want to learn, then everything else cannot be a variable, it has to be constant. So the how fast it changes has to be constant, that's the half-life of carbon-14. What we have is obviously what we have, this is never in question. And how it started is a problem. We don't know what the atmosphere was like, because that's what we're looking at here. We're always assuming that the carbon in a rock sample was trapped from the atmosphere when it formed. And so diamond is a good example. I've brought that up already. Diamond is just a network of carbon, pure diamond is, carbon atoms. And it does not capture more carbon. However it forms, once it's formed, that's it. You've got the carbon that was in the atmosphere the moment it formed is the carbon that it's stuck with. And then, because there's a mixture of C14 and C12 in the atmosphere, there's going to be a mixture of C14 and C12 in the diamond, and then over time, the C14 is going to decay into C12, and that's how you use carbon dating. Carbon is useful not so much for diamonds really, but for living things like fossils, because all life as we know it is based on carbon atoms. If you look at the polymer chains that make up your skin, you're going to find a whole bunch of carbons all bonded to each other in a big long chain, and then there's a bunch of other stuff sticking off of it that makes it work in different ways. But carbon is the basic atom for all life. So having a way to date using carbon is a good way to date things like fossils and other living matter. And so that's why you hear about carbon dating, is because it's useful for dating dead things. Things that had, they were breathing, they were getting that carbon into their body from the carbon dioxide in the atmosphere, and then they die, they get buried, no more access to the atmosphere. The carbon in that dead body / fossil is the carbon that was in the atmosphere the moment that it was covered. And so if we pretend like we know this, then we can tell how long those things have been dead. The problem is that we don't know this. We have no way to know this, except by circular reasoning. For example, finding a diamond buried in a rock layer that we assume is 50,000 years old, then we would say, using our math, we can figure out how that atmosphere must have been 50,000 years ago based on the composition of that diamond, which we supposedly know is 50,000 years old. But if our assumption that it's 50,000 years old is wrong, then everything else that's based on that assumption comes tumbling down. And that brings us to dinosaurs, which we talked about a little bit. I must be an anomaly because I don't find dinosaurs interesting at all, but everybody else does. Dinosaurs are just one brand of fossil that has been buried in the earth. And you can use carbon dating to try to figure out how old these fossils are, or if it's too old for carbon dating, you can use other kinds of dating, but the dating assumptions are always going to be bad. So yeah, and then we talked about how, sin is destructive, and so it should be no surprise that dinosaurs and lots of other things have gone extinct, because extinction does not violate God's story at all. It's sad, it's bad, but it's not impossible. In fact, it's expected. You should expect things to go extinct. What's unexpected is that life on Earth has lasted as long as it has, given how much death on Earth persists. But that's not a scientific statement, that's a theological one. Andrew?
So, do animals go to heaven?
Do animals go to heaven? That's definitely beyond the scope of this course. The Bible doesn't say they do, like specific animals, but it also talks about animals being in heaven. So, like, if Fluffy the Wonder Dog, needs to be in heaven for you to be happy there, then God will give you Fluffy the Wonder Dog in heaven. And that's all I can really say about it. What's that, Isaac? Who's Fluffy the Wonder Dog? Oh, let me show you some pictures sometime. I'm just kidding. All right. Are there any questions about this stuff? This dating business? All right. Next time, I'm probably just going to go into page 61 in your book, which is about evolution. So we've talked about the age of the Earth. We've talked about radiometric dating methods. The next big thing I want to tackle is the biological theory of evolution. So here is a thing. I forgot to change the heading on half of them, so I'm sorry about that. You get to read another article for your homework tonight.
That's actually fun. I like that.
Good. Yep, this is from the same organization. It's called Answers in Genesis. They just produce a lot of really good stuff. And this article is just 6 very briefly explained evidences of a young Earth, which is what we've been talking about, so it fits perfectly. Good night.